Welcome to The Explainer. Today we are jumping into one of Irodov's legendary physics problems, specifically number 1.82. We're going to take this really complex system and break it down step by simple step. If you've ever looked at a problem with wedges and blocks and pulleys all moving at once and just thought, where do I even start? You're definitely not alone. It's a classic sticking point. But trust me, there is a very clear, very methodical way to solve these things. So here's our challenge for today. We've got a bar, let's say it has a mass m, sitting on a wedge of mass m. Now this bar is tied to a wall with a thread that goes over a little pulley. We're told the whole system is frictionless. So when you let it go, the bar slides down the wedge, and that causes the wedge itself to slide to the right. Our mission, should we choose to accept it, is to figure out the acceleration of that wedge. To get this done, we're going to use a simple 4-step battle plan. And the cool thing is, this isn't just for this one problem. You can use this exact same approach for pretty much any tough mechanics problem that gets thrown your way. Okay, first things first. Before we can do any math, we have to play detective. We need to identify every single force acting on every single object. Seriously, getting this part right is the foundation for everything else. So let's draw what we call free body diagrams. On the bar, it's pretty straightforward. You've got its weight, mg, pulling straight down. You've got the normal force, N, from the wedge, pushing up at a right angle to the surface. And you have the tension, T, from that thread pulling up along the incline. Now for the wedge, it has its own weight, mg, and the ground pushing back up on it. But here's the crucial part. It also feels the forces from the bar. The bar pushes back on the wedge with an equal and opposite normal force. And the thread, because it's wrapped around that pulley, pulls the wedge horizontally. All right, step 2. This is the one people often forget, but it is the absolute key to unlocking this whole problem. We need to find the constraint, that hidden rule that secretly connects the movement of the bar to the movement of the wedge. Just think about it for a second. That thread connecting the bar to the wall can't stretch, right? It has a fixed length. This means that as the bar slides down along the slope, the horizontal distance the wedge moves has to be directly related. They can't just move independently. Their motions are tied together. This geometric connection is what physicists call a kinematic constraint. It's not a force. It's a rule about the geometry of the whole setup. And finding this relationship gives us a brand new equation that links the bar's acceleration to the wedge's acceleration. Without this equation, we'd be stuck with too many unknowns to solve the problem. It's the missing piece of the puzzle. Now we're at what I think is the most important strategic decision of the entire problem. Before we even think about writing F equals ma, we have to choose our point of view, a reference frame. And believe me, this choice can make the problem either beautifully simple or an absolute nightmare. Now, the most obvious choice is what we call the ground frame. Just imagine you're standing still, watching the whole thing happen. From this perspective, the wedge's motion is simple. It just slides sideways in a straight line. But what about the bar? Its motion is a messy combination of it sliding down the wedge while the wedge itself is moving sideways. If you stick with the ground frame, the bar's total acceleration becomes this complicated vector sum. It's the wedge's acceleration plus its acceleration relative to the wedge. This right here is a classic pitfall. It is so easy to get tangled up in all the vector components and make a small mistake that throws off the entire solution. So let's ask a much better question. What if we just change our perspective? Instead of watching from the ground, what if we imagine we're sitting on top of the wedge, riding along with it? This is a pro tip, and it can simplify things like you wouldn't believe. Now, because the wedge is accelerating, this moving point of view is what's known as a non-inertial frame. And here's the catch. Newton's famous laws don't quite work here. At least not without a little tweak. To make them work, we have to invent an extra force, a pseudo-force. You can think of it as a correction factor we have to add just because our point of view is accelerating. And here is the big payoff for that little trick. From the wedge's point of view, what does the bar's motion look like? Well, it's just a simple, straight-line slide down a stationary ramp. That whole complex vector problem, it's gone. The only price we pay for this massive simplification is adding one extra force on the bar, this pseudo-force, which points opposite to the wedge's acceleration and has a size of m times that acceleration. Okay, we've identified our forces, we've found our constraint equation, and we've made a really clever choice of reference frame. Now we are finally ready to put all the pieces together and actually solve this thing. So here's our final setup. We're going to apply F equals ma to the bar, but we'll do it in the accelerating frame of the wedge, where the motion is simple. We just have to remember to include that pseudoforce. Then we'll analyze the wedge itself, back in the simple ground frame. This kind of hybrid approach gives us a nice, clean set of equations that we can solve together with our constraint equation. And after we do all the algebra, this is what we get. The acceleration of the wedge, let's call it W, is given by this expression. And it makes sense, right? It depends on the masses of the bar and the wedge, the angle of the incline, and of course, gravity. Now, getting the right answer is fantastic, but the real victory here is the method. What you've just seen is a powerful, systematic way to think your way through a tough physics problem. So let's just recap that battle plan, because this is your new superpower for these kinds of problems. Number 1, diagram all the forces, don't miss any. 2, find that hidden kinematic constraint. 3, make a strategic choice about your reference frame, and don't be afraid to use an accelerating one. And finally 4, write down Newton's laws and solve the system. Look, if you only remember one thing from this explainer, let it be this. The hardest part of a physics problem often isn't the calculus or the algebra, it's choosing the right way to look at it. A clever choice of reference frame can literally transform a horrible mess of vectors into a simple, straightforward calculation. So now start thinking about where else you can use this technique. Any problem that has an accelerating elevator, or a block on a moving cart, or some weird pulley system. Start asking yourself, wait a minute, could I make this problem way easier by just hopping into a non-inertial frame and adding a simple pseudoforce? You might be surprised how often the answer is yes.